If you were going to look for one single book on using isotopes in catalysis, I guess my choice would be one that the next speaker has written. And so it's a pleasure to have a presentation on the diagnostic use of deuterium and elucidating mechanisms in catalysis by Professor Ozaki.
It is a great pleasure to be here to talk about the isotopic study of heterogeneous catalysis. I spent a year and a half at the pre-chemical laboratory of Princeton University from 57 to 59 and worked on ammonia synthesis. This work was presented at the Gordon Conference of 59 and by Hugh Taylor. He is a co-worker. Since then, I had a chance to give a talk at the Gordon Conference at 69 or 70 and again at 79. So I had a chance every 10 years to give talk in this country, and this year 89. So every 10 years I'm giving. So I would expect another talk at 99.
Quarter.
Today my talk is a review of past work on isotopic studies. Among them, ammonia synthesis work, deuteration of ethylene, and reversible part of hydrogen absorption as revealed by tracer gas chromatography. And finally, origin of inverse isotope effect. Deuterium was found in 1932, I think, and right after the discovery, Professor Taylor was given a small amount of deuterium. So we used this for the useful device for the elucidation of mechanism. At that time, Jungas, Morikawa, and Powell was in the school, or Taylor School. And first, in this slide, the mechanism of ammonia synthesis reaction was examined by ammonia deuterium exchange. This was found at room temperature, even at room temperature. All those ammonia synthesis should, the temperature of ammonia synthesis must be raised to 400 degrees centigrade. And on the other hand, isotope exchange reaction between dinitrogen requires high temperature. In this way, dissociation of hydrogen and exchange with ammonia, these steps thought to be equilibrated or very fast. as compared to the dissociation of dinitrogen. In this way, thinking PCF scheme published in 1940 was qualitatively expected by these two reactions, two exchange reactions. Another impressive result was the deuteration of ethylene by Takevich, published in 1950. At that time, everybody expected to give ethane D2 by reaction of ethylene and deuterium. But unexpectedly, the first product was D0 ethane, right ethane, and C2H3P. This unexpected result was explained in terms of polyoliptic Prani mechanism, in which absorption process step of ethylene and addition of hydrogen atom to ethylene adsorbed to give ethyl intermediate is very fast as compared to absorption of hydrogen. And by equilibrium position, equilibrium is quite shifted to ethane, so that no backward reaction over here is very few, very small contribution of backward reaction, so that the rate of hydrogenation is determined by rate of hydrogen absorption, but also formation of ethane is same rate as compared. These steps are very rapid. This situation is simulated by this figure. You have a water tank over here and small stream of water came into this tank and flow out from here. If you put the dye into the entrance without agitation over here, then you may have piston flow of dyed water. But if you had agitation or star over here, then the dye will disappear over here by dilution with a large amount of water, so that the very dilute flow of dye come out. The situation is like this. Introduction of hydrogen over the nickel surface covered by ethylene is limiting the reaction, and introduced hydrogen is quickly diluted by ethylene with this reversible rapid reaction, so that giving a dilute ethane in the initial state. by using deuterium as a tracer, you can have a image of relative rate of elemental reactions involved in one act of catalysis. This is a very good example of the relative rate estimation. In that case, rate of hydrogen absorption is very limited, limiting the hydrogenation of ethane. In the absence of olefin, when you flow hydrogen over metal catalyst, then you may expect hydrogen repeat absorption, desorption along the catalyst bed. But if you put helium in the stream of hydrogen, then helium goes through without absorption. So I thought if you put deuterium as a parus in a hydrogen carrier gas, then deuterium repeat traces this route if you have a reversible absorption over here. But without a reversible absorption, then deuterium parus may go through along with helium. So we initiated deuterium gas chromatography using hydrogen as carrier gas. And at liquid nitrogen temperature, retention time of deuterium is very large as compared to helium. This means deuterium is adsorbed, repeating absorption, desorption, so that give retention. But at minus 90 degrees centigrade, deuterium come out same time as helium. This means although hydrogen is chemisorbed or adsorbed, the flowing hydrogen does not absorb. At more higher temperature, again, this deuterium peak give us small amount of retention and increasing with temperature. But in this time, eluting Rs gives hydrogen HD instead of G2 at low temperature. This means this slide shows amount of absorption plotted against temperature. Dotted line gives you total amount of absorption as observed by simple volumetric method of absorption. And solid line gives you reversible part of absorption as observed by retention. So at liquid nitrogen temperature, reversible part of absorption is very large, but by increasing temperature at about 100 degrees centigrade minus this reversible part is assumes 0. And again, increasing with temperature, giving HD in April. So this result shows you adsorbed state of reversible adsorption at lignite temperature is diatomic, molecular, and activated adsorption comes out from around this temperature and above. In this way, total amount of absorption of a nickel may be fully reversible at 0 or 273 K. In this way, deuterium chromatography in a hydrogen carrier can give you a reversible path of adsorption in a flowing hydrogen. The next topic is the inverse isotope effect. As I told you, in 1957 to 59, I found the inverse isotope effect in ammonia synthesis. But before that, in 1945, Ruiten and Jungers published that deuterium was faster than hydrogen or nickel to give methane. But this time, at this time, no explanation was made. In 1955, Weiberg stated that introduced many examples for acid cation reaction in a homogeneous system. In this case, D2O homogeneous acid cation reaction proceeds more readily in D2O than in H2O. In 1957, Yamada published work on the vinylation of acetic acid to give vinyl vinyl acetate. In this reaction, deuteroacetylene reacted faster than right hydrogen acetic. Also, in this case, no explanation was made. And in 1960, we published ammonia synthesis work. In this case, the result was explained in terms of thermodynamic isotope effect on the adsorbed species. Amount of adsorbed species has a large amount of adsorbed species in hydrogen system. So isotope effect was found on the thermodynamic equilibrium on the amount of adsorbed species. Since then, many results was reported on the hydrogenation of carbon monoxide, in which deuterium reacts faster than hydrogen. And more recently, these results are summarized over here. In case of ammonia synthesis, 3 to 4 times faster for deuterium than hydrogen. In case of carbon monoxide, about 1.3 to 2 times faster reaction has been observed for carbon monoxide hydrogenation over ruthenium, nickel, palladium. And in case of isomerization, skeletal isomerization of normal hexane, 2.5 times faster rate for deuterium system over platinum, and for hydrogenolysis over platinum. This inverse isotope effect can be explained by 0-point energy difference. 0-point energy differences increases as hydrogen forms a compound. For instance, in case of hydrogen, 1.8 kilocalorie per mole hydrogen is increased to water H2O 3.6 kilocalorie, for ammonia 3.8, for methane 3.5, and in case of chem-solved hydrogen, hydrogen atom, this is estimated to be 2.5 kilocalorie per mole hydrogen. So, if you form a compound, zero-point energy difference is increased as you change from H2 to B2. Inverse isotope effect observed for ammonia synthesis or carbon monoxide hydrogenation is largely traced back to this 0-point energy difference. This gives rise to larger heat of absorption for the intermediate. When a reaction of the adsorbed intermediate is rate determining state, the 0-point energy difference can be the same with the activated complex as with the adsorbed intermediate. This means this 0-point energy difference in the reactant molecule is enlarged in the adsorbed state, and this change, this difference is maintained in the activated state because this CHO, NHO, OH bond is not cleaved at the rate determining state, so that this difference is maintained at the activated state also. this way, low activation energy is found with deuterium. So RD is larger than RH. That is inverse isotope effect is come out. This means that the origin of the isotope effect is thermodynamic in nature. For instance, in case of carbon monoxide hydrogenation, if the isotope intermediate is the MCH4H and this is equilibrated, and the dissociation of this CO in the redetermining step. In this case, the rate is faster in deuterium system. But in case carbon monoxide is directly attack of hydrogen to carbon monoxide is determining step, then isotope effect would be normal. So, summarizing the result, deuterium can be successfully used to elucidate the mechanism of catalysis, and some example is introduced over here. Thank you for your attention.
We have time for a question if there is any. Joe?
Mr. Ozaki, in using a thermodynamic origin for the inverse isotope effect, does that include the possibility of more deuterium being absorbed than hydrogen? And that's really the origin, another way of looking at the same thing.
Yeah.
That it's the thermodynamic effect that leads
Yeah.
to more
Yeah.
absorption.
Well,